And finally, we come to the last part of the calculation, which is calculating the Wood mean square speed of gas molecules, CRMS, or we can just say as simple C here. The meaning are the same. Then let's look at the question. We have some oxygen gas and hydrogen gas with two identical containers. That means they have the same V here, and then they have different mass. Hopefully, if you study chemistry, you know that they have different molar mass. But if you don't, still you should have this common sense, because we are now talking about some qualitative stuff only, so that you have to know that oxygen is heavier than hydrogen gas. And to be more exact, the molar mass for oxygen is equals to 16 gram per mole, while for hydrogen is 1 gram per mole. But then this is a gas molecule, so that you can see O2. That means two oxygen molecules combine to form a oxygen gas. Two oxygen atoms combine to form a oxygen gas molecules. So that the molar mass times 2 will be the molar mass of the gas. Okay, but at least you know that oxygen is heavier. At least. And then both gases are at room temp. That means they share the same temperature and same atmospheric pressure. Which one is true? The number of mole of gas molecules is the same. Then we want to know N, so that we try to rearrange N to be the subject. Then N will be equals to PV over RT, because PV equals to nRT. And then we try to look at the situation. They share the same P, equal V, because identical container, and then equal T, while R is a constant, so that your conclusion will be the number of mole must be equal. Therefore, Na must be equals to N boy. They share the same amount of molecules. Even one of it is heavier, one of it is lighter, but it doesn't matter, because in the equation of PV equals to nRT, we can't see any m inside, small m inside. That means it doesn't matter. Next, the Wood mean square speed is the same. Then you really have to think of the equation. Let's try to derive it again quickly. The average Ke is in fact equals to half mc squared, which is 3RT over 2Na. We recite it, and we can also copy it from the formula sheet. Now, we try to find out what is C. By a simple change of subject, we can find that C is this, which is directly proportional to T over M. This is what we have in mind. And every time, we will be thinking of this in these examples. Okay, then that means the Wood mean square speed is directly proportional to T over M. Then let's look at that. T is the same, equal for both, while for M oxygen, M oxygen is heavier than M hydrogen gas. So that if oxygen is bigger, for example, then the CRMS for oxygen will be smaller. So that our conclusion is CRMS for oxygen gas will be smaller than hydrogen gas. Then this is not a correct statement, because it is not the same. The heavier one is slower. And lastly, for statement 3, we talk about the frequency of collision. Then are they the same? Then we have to talk about the microscopic view of that. We have the same volume for both container, right? And just now we have deduced that the CRMS for oxygen is smaller than the CRMS for hydrogen. That means oxygen molecules are moving slower, okay? And because they got the same volume, right? So that you can conclude that the frequency of oxygen must be smaller than that, because they have to travel, right? They have to travel in this way for the molecules. And hydrogen is faster, so that oxygen will have less frequency. Then they are not the same, but should have less frequency. Then the answer should be A here. Next question. Container X holds some hydrogen gas and then Y holds some oxygen gas, similar to the previous case. Now if the hydrogen molecules have the same RMS speed as the oxygen, what is the conclusion? What is the conclusion of that? Then again, we have to think of same C here. And then we have C is directly proportional to T over M square root, right? And now what we have is C will be equal for both. So that, for example, for oxygen, the mass for oxygen is higher. Then in order to keep C the same, then T must be also increased in order to have the same root mean square speed. That means the oxygen gas must be hotter so that the heavier oxygen molecules can be moving faster. Because originally, if it is heavier, it will be slower. Then this is our conclusion. Then with this, we try to choose our our statement. The gas X, which is hydrogen, higher temperature. No, it should be gas Y got a higher temperature. Gas X is at higher pressure. In fact, this is not related to what we are talking about, because if we talk about pressure, then we have to use PV equals to 1/3 nmc square. But then we got no information about V here. We have no information about N at the same time, so that we really can't conclude what is the pressure. Same here, not related because of the same reason. And they get the same temperature, must be wrong, because the oxygen gas must be hotter. Next, two vessels contain, again, hydrogen, oxygen, and both gas are assumed to be ideal gas. They have the same pressure, and temperature the same, which accordingly must be the same at the same time. Then for A, we want to talk about volume. Then we make volume the subject as usual, nRT over P. Okay, and then we look at R to be constant, T to be the same, P to be the same. But then we don't know anything about small n. Therefore, we can't conclude the information about V. Not sure about the information of V. Boy, so that this is not a must. The mass per unit volume. Mass per unit volume means m over V. Somehow like the density. Then we have to think of an equation that got V and M at the same time. Then we have PV equals to 1/3 nmc square. And we want mass per unit volume, right? Here the mass means the total mass, so that it should be nm over V. Okay, then we have nm over V here equals to 3p over c square. Again, 3 is a constant, p is equal, and about c. C is about the temperature and also the mass of molecules, right? And here T is the same, while mass is not the same. This one is not the same. So that C is not the same. That means this mass per unit volume not the same. This is also wrong. Next, C. RMS speed. We have mentioned already, C is directly proportional to that, and this is not the same, this is equal, so that C not the same. And lastly, number of gas molecules per unit volume. Number of gas molecules per unit volume. That means we want to have N over V or N over V. They are the same because this is just having the Avogadro constant in between. So that we want small n over V. Then we think of another equation again, which is PV equals to nRT. And then N over V is what we want, which is P over RT. Next, P is the same, T is the same, R is constant, so that they share the same N over V. That means this is the answer. D is the answer. Next, we have two containers connected each other, and then initially this is closed, and then we have some pressure here, and we don't want kPa, we want Pa, so that you directly change it to Px is 400 times 1000 Pa. This is what we want. And then evacuated, that means vacuum, that means no molecules inside. And then now it's open, and then we wait for the equilibrium. Then you have to know that the direction of flow is depending on the pressure, so that we have a high pressure within X while we have zero pressure at Y, so that the molecules will move from X towards Y. Then what is the meaning of equilibrium? Will be at the end when they have the same pressure only, not about number of molecules. As long as they have the same pressure for both containers, then this is the meaning of equilibrium. Okay, then this is our idea. Now what we want is, firstly, the gas pressure at X is 100 kPa. That means we want to find out the final pressure of the whole stuff. Okay, so that firstly we will stick to our basic. We look at the initial situation first before opening. That is Pxvx equals to nRtx here. So that when we put in all the number, this is V equals to Nx and then RT. Here we have to assume that this is a constant temperature because we have a metallic container, so that this will be always the same temperature as the surrounding because it is metallic, not insulated. So that this metallic container help us to think of this is a constant temperature with the surrounding for the whole process. So that now we have T as the temperature. Then Nx will be equals to 400,000 over RT. 400,000 V over RT. And then we will talk about the equilibrium state. That is, for the whole XY, we again choose PV equals to nRT, PV equals to nRT for the whole, so that we will have the new P prime, and then V is 5V equals to still the same Nx because there is no molecules in Y, so that we just put in what we have for Nx, and then RT, still the same T because it is always the same with the surrounding. Then we can have some simple cancellation and resulting in this new pressure for the whole. So that this is wrong, it should be 80,000. Are still gas molecules moving through the tape S. That means at equilibrium, is there any gas molecules moving through S from X to Y or from Y to X? The answer is yes. This is called dynamic equilibrium. That means the gas molecules are still moving, but then the speed of moving from X to Y is equal to the speed from Y to X, so that they are dynamically equilibrium. They're still moving, but then the net is zero. Next, the product of pressure, that means times, pressure and volume of the gas in X is equal to that in Y. That means we want to know PV for X is it equals to PV for Y. Then what we have is they have the same pressure at the end, right? But then they got different volume. One is V, one is 4V. Okay, so that's PXV X will be equals to the same pressure P and then V, right? And then on the other hand, P Y V Y is equals to the same P, but then 4V for Y. Then obviously they are not equal. Obviously. So that this is wrong. The density in X is greater than that in Y. If we want to talk about density, that means the number of molecules per unit volume. Then we talk about N over V will be equals to P over RT here. Number of molecules over volume is the density. Then they got the same P, they got the same T, R is the same, so that they will have the same density. So that it is not greater, but the same. Lastly, the gas molecules in Y on average move faster. That means we want C, the Wood mean square speed. Then you know that we have same temperature leads to same Wood mean square speed. That means the same average speed at the same time. So that not move faster but the same. The answer should be boy. Next, a fixed mass, number of mole the same. Ideal gas at STP. STP is the short form of standard temperature and pressure. That means we have the room temp and normal ATM. That means 100 kPa around, okay? But then it doesn't matter because you don't need to have exact number, and you can't assume room temperature to be 25, and you can't assume 1 ATM is 100 kTP. You just know that they are a particular amount, okay? And now we have the original V, now is heated, temperature increase, and allowed to expand, volume increase, so that this is the new volume, V1 and V2 here, with pressure double, so that we have P2 is in fact 2P1. Then the Wood mean square speed, we want to know how to change C here. Then you have two ways to do it. One way is to use the ratio directly proportional to square root T over M. But then usually we don't feel comfortable with some ratio stuff. So that if you're good at that, then go on. But if not, then we are going to use the exact equation, which is C is square root 3RT over NAM here. That we can easily derive. But then this time we don't have any idea about RT, but then we have the idea about pressure, right? So that we may further change it to by PV equals to nRT. We further change it to 3PV over NAMN. You can do it in this way. Okay, then we are using this because we know the P and V situation. Okay, so then now this is the old one. The old one is 3P and then 2 NAMN. They're all constant. And now we got the new one, which is 3P4. Sorry. P is changed. 3 and then 2P and then 4 and NAMN, which is all the same. Then you can see that this one is in fact the double of it, because now you may try to put it in this way. That is 3P. Here you may calculate 6 here. And here you have again 6, but then you will have a 4, additional 4 here, so that when this 4 take out from the square root, you got 2 of the original. That means the root mean square speed will double. Next, we're looking at the relative atomic mass of oxygen is 16. What is the ratio of RMS speed C of oxygen to that of hydrogen? Then some of you may be a little bit worried because you don't study chemistry, so that we really don't know what is the meaning of relative atomic mass is 16. And then what is the relative atomic mass of hydrogen? I really don't know. I think it should be okay because in DSC they must give you more information, or they may not give you exact number. They may give you a ratio directly of the mass of molecules for oxygen and hydrogen for calculation, so that it's okay. But now I want to give you some more information so that you feel a little bit more comfortable while you are doing this type of question. The relative atomic mass is 16. In fact, this is the meaning of we got 8 proton inside and also have 8 neutron. And in fact, you have 8 electron, but then it doesn't count because the mass of electron assumed to be 0, very, very small when compared with proton and neutron, so that we don't care. Then 16 is from 8 plus 8. Then how about hydrogen? Hydrogen is 1 proton plus 1 electron, but then we don't care about electron, so that the mass, our relative atomic mass of hydrogen is 1, while oxygen is 16. But then, furthermore, we are talking about oxygen molecules, so that oxygen does not appear as atom, but O2, right? So that the molecules is in fact relative atomic mass of 32 and also 2, because double, okay? And then at room temperature, that means they share the same temperature. Okay, so that this time I try to not using the exact equation. Last time we used the exact equation, right? We see a lot of things here, but then here we may try to directly use the ratio stuff, see if you are okay. Then they got the same temperature, so that we further conclude that in this case only, the CRMS is directly proportional to square root of 1 over m. And now we want to have the CRMS for O2 and H2 so that we can have this ratio. Here we use small m. In fact, small m is not exactly equal to the relative atomic mass of 16 because one molecules, the mass of oxygen molecules is very, very small, so that it is not directly equal to 32, but then they are directly proportional to 32. Okay, so that we can still somehow use it in MC directly to put in 32 here and directly to put in 2 here. It doesn't matter if you can't think of molecules as having O2, still you can put in this in, and it will be totally okay. That is, you put in 16. Is exactly the same. Okay, then we have simplified version of 16, which is 1 over 4 here. That means the hydrogen molecules are moving 4 times faster than the O2 molecules in general, because it is the root mean square, somehow the average, one of the calculation method for average. Okay, in average. Okay. Next, this time we really got some ratio. Okay, 2 different ideal gas, AB, in identical vessels, so that they share the same V, and the ratio of the temperature is this, so that we have TA to TB is this 2 to 1, and the ratio of root mean square speed CA to C boy is 3 to 1. What is the ratio of the molecular mass? That means we want to find MA over MB ratio. Be careful, this is not, MA is not exactly as their molecular mass. This is the mass of one molecule, but then it is okay because this is just a ratio of the mass. Then we can think of, this time I try to use the exact equation, like CA is equals to the square root of 3RT over NaM, right? And then we put in some A here. On the other hand, C boy is in fact equal to square root 3RT over NaM for boy. And we want to know the ratio, so that this one over that one will be the ratio. That means we remove the equal sign and put in here. Then this is Ca over Cb, which is that stuff over that square root stuff. Then we can have a lot of simplification here. And now we have this to be equals to the ratio 3 to 1. That means this is equals to 3. Now we further simplify, we take square for both sides, then we have Ta over Tb, and then Mb over Ma equals to 9. Then Ma over Mb, we can have some rearrangement, will be equals to 2 over 9. Then the answer will be boy here. Next, a first similar situation, we have a temperature here, not in Kelvin temperature, so that we change it directly, and then fixed mass. We have C as the root mean square speed. Now increase the temperature. T is now changed to new temperature. Then what is the new C prime? Okay. Then this time again this time I try to use two methods to help you to fix this problem. The first method is again using the exact equation, so that we have 3 RT over NaM square root, and then we try to put in some more number, which is this for temperature. We don't know M, but then because we are using the same gas, so that M, small m is the same. And then the new one, the new C, is square root 3R160 plus this times this over this. Alright. Then how to really change this in terms of the original C? We may try to add in this to help us. Sorry. We want this to appear, so that we create this one. And in order to solve the problem of creating, we divide this again. Okay, we create this and this. So that the first stuff, this first stuff, will be C. Okay, so that we can try to press our calculator and try to press this stuff by calculator, then we will be able to get 1.1 C. Okay, which is the answer D. If you don't want this, thinking of this to be a little bit complicated, then you may also think of the ratio stuff. C is directly proportional to square root T over M, right? And then here M is the same because we are using the same gas, so that we can conclude C is directly proportional to square root T. Then the new one over the old one will be equals to the new T over the old T. Then we can have directly this and get 1.1 here. That means C prime is 1.1 of the old one. Then you can see that this is simpler, but then you need to be having some more advanced skill in math to deal with the problem of directly proportional, and then you can successfully set this up. If your math helps you to do this comfortably, then this is very okay method and faster method. Finally, we come to the last page of the note. We have a fixed mass, that means N is kept constant, of an ideal gas is contained with a container of frictionless piston. That means, in fact, the hidden information is pressure to be constant here. And then the gas is being cooled. Temperature decreases under constant pressure. Then it helps you to understand what is the hidden information. But then, if it doesn't mention constant pressure here, still you know the hidden information from frictionless piston. Next, we want to know that the average separation will decrease. That means, in fact, we want to know the volume situation, because the number of molecules is a constant, then when the volume decreases, the average separation will decrease. That means we want to know V. Then we may use R equals to PV over NT, which is a constant, to help us. Then let's look at different things here. P is kept constant. V is what we want. N is a constant, and now the gas is being cooled, so that V has to decrease in order to keep everything constant. Therefore, we know V decreases with number of mole the same. Then the separation, average separation, will decrease, and further the density will increase, but it is the extra stuff, so that the separation decreases is correct. Next, for statement 2, the root mean square speed will decrease. Then we talk about C directly proportional to T over M square root, and then we know that M is constant because we are using the same gas, the mass of molecules the same, while temperature is cooled, so that the whole stuff will decrease. Therefore, C decreases. This is also correct. And lastly, the number of collisions per second will decrease. That means we want to talk about the frequency here. Then we have to talk about the microscopic stuff. Now what we know is the pressure is the same, kept constant, while the change in momentum is in fact decreased because the temperature decreases, so that's the change in momentum, the speed is decreased. Then in order to maintain a constant pressure, what you need to do is your frequency must increase in order to maintain the constant pressure, so that the pressure should in fact increase. This is wrong. The frequency should increase, right? Then the answer should be A here. Next, which of the following situation about the root mean square speed of a fixed mass increases? We want this to increase. Then how to increase it? You know that C is directly proportional to square root T over M. And now with the gas heated, temperature increases with constant volume. Then you know this is constant and this increases, and C increases, so that this is correct. Next, we again think of C T over M square root, and now this time is gas expand, volume increases under constant pressure this time. Now nothing related to temperature, so that we have to know what is the temperature change. Then we have to further think of R is equals to PV over NT, which is a constant. Then when P is the same, V increases, N is a constant, then T has to increase in order to keep everything constant here, so that T increases, M constant, then C increases at the same time. Okay? And lastly, this is a constant pressure, a constant temperature, then you don't have to think of it anymore. If the temperature is constant, then C must be constant at the same time, given that M is a constant. Then this is wrong, then the answer must be C. Finally, the very last question. This is the latest DSE 2017 question. It is given that the average K is this number, this equation, which is also in the formula sheet, and then now we have a monoatomic. That means one kind of gas only, not a mixture. One kind of gas only is heated from this temperature to that temperature, T1 and T2, under fixed volume. Then firstly, you estimate the ratio of the root mean square speed. That means C here at 2 temperature, and in fact we have done that before. Then we can be a little bit quicker to put in everything here. The C for 350K over C for 300K. We try to be quick to put in everything all in place. Then we have 3RT over NAM over 3R another T over NAM. Then we directly simplified it by cancelling the similar stuff, and directly gets the ratio to be 1.08. Okay? And B, we further use the kinetic theory to explain why gas pressure will increase when we increase the temperature while keeping the volume the same. Then here we got 2 marks. Make sure you use the physics terms. As the temperature increased, the average speed of the molecules increases. With volume fixed, the molecules will hit the wall of the container more frequently and violently. Therefore, the pressure increases. Okay? Therefore, you have to say what is being changed and what is the effect of changing, and then what is being fixed. Then with these 2 effects combined, then it will hit more frequently and violently. And therefore, this is our conclusion. And